Welcome to the first video in our thermodynamics series. In this video, I am going to focus on Hess's law in particular and cover our objective of applying Hess's law to thermodynamic equations. In class the other day, we discussed the idea of a state function, that is, a property that is independent of the pathway. We also stated at the time that the change in energy in a system is a state function, as is enthalpy. Because it is a state function, the change in enthalpy from one initial state to some final state can be calculated regardless of how many steps are required to go from an initial reactant to a final product. And this idea is the basis behind Hess's law. My first example for Hess's law is a relatively simple one. The top reaction on the slide has a change in enthalpy of 68 kilojoules. Nitrogen gas plus 2 oxygen gas yields 2 NO2. Now those two lower step reactions combine algebraically to equal that first one. The change in enthalpy associated with each of those steps also algebraically add up to that overall reaction. As I said though, this is a straightforward a straightforward example. Sometimes the reactions involved in the steps need to be manipulated somewhat in order to achieve that final reaction. So let me show you what I mean. There are some rules for manipulating these reactions. Sometimes a reaction involved in the steps needs to be reversed in order to calculate the change in enthalpy using Hess's law. If it does, the sign on the reaction must change. In other words, a reaction that is endothermic in the forward direction must be exothermic in the reverse direction. Therefore, if the reaction is reversed, the sign must change. The magnitude of the change in enthalpy is directly proportional to the quantities of reactants and products in a reaction. If the coefficients in a balanced reaction are multiplied by an integer, the value of the change in enthalpy is multiplied by that same integer. In other words, if the reaction needs to be doubled, then the change in enthalpy must also double. If the reaction has to be divided in two, then the enthalpy must also be divided in two. Let's do a basic example problem for Hess's law. This example is on page 253 in your textbook, and I highly recommend that you follow along in your textbook on this example problem and the one after. Two forms of carbon are graphite, that soft, black, slippery material used in lead pencils and as a lubricant for locks, and diamond, the brilliant hard gemstone. Using enthalpies of combustion for graphite, negative 394 kilojoules per mole, and diamond, negative 396 kilojoules per mole, calculate the change in enthalpy for the conversion of graphite to diamond. Since the enthalpies of combustion were given for graphite and diamond, let's start by writing those equations. In this case, the combustion of carbon yields CO2 for both reactions. The idea behind Hess's law is that we can manipulate these two-step reactions to yield the overall reaction of graphite to diamond. If you look at the overall reaction, graphite is the reactant. So we want one of our step reactions to also have graphite as a reactant. And the first step reaction allows for this. Now if you look at our overall reaction again, it has diamond as a product. Our second step reaction has diamond, but it is as a reactant. So we must reverse that reaction so that the overall reaction and the step reaction products line up. Now that the second reaction is reversed, the reactants and the products both line up with our overall reaction. Note that when the second reaction was reversed, the sign was also changed. There is just one more thing that we need to do here. Since the first step includes oxygen as a reactant and the second reaction produces oxygen as a product, oxygen is considered a catalyst and it is not a part of the overall reaction. It is on both sides of the equation and therefore oxygen molecules can cancel. Along the same line, CO2 is produced in the first reaction and then consumed in the second. CO2 is not a catalyst, it's what we call an intermediate. It also exists on both sides of the reactions and is canceled as well. The two reactions add up to the overall reaction and their enthalpies are added together. Therefore, 2 kilojoules is the change in enthalpy of the overall reaction. Let's try one more example problem. This one is a little more involved. Diborane, B2H6, is a highly reactive boron hydride that was once considered as a possible rocket fuel for the U.S. space program. Calculate change in enthalpy for the synthesis of diborane from its elements according to the equation. 2 boron solid plus 3 hydrogen gas yields diborane. Use the following data. And the problem gives us 4-step reactions as a possible solution to this Hess's Law problem. I included the overall reaction at the top of the slide. The following 4 reactions can be manipulated in order to add up to this overall reaction. To work a Hess's Law problem like this, I usually use a systematic approach. I move the reactions around to align with each of the substances in the overall reaction one by one. For example, boron solid is the first reactant in the overall reaction, so I will look at my step reactions and find the boron solid. The first step reaction has boron as a reactant and in the right quantity, so the first reaction does not need change to align with my overall reaction. The second reactant in the overall reaction is hydrogen gas. If we look at the third step reaction, it has hydrogen gas as a reactant, but I need 3 in the overall reaction, not just 1. So the third step reaction is multiplied by 3. Remember, as the coefficient changes on the hydrogen, it also changes for all of the substances, and the enthalpy change too. The overall reaction only has 1 substance left. I need diborane as a product. The second reaction has diborane, but it is currently a reactant. So the second step will need to be reversed. And as with the first example, if the reaction is reversed, the sign on the enthalpy must also change. Now that all the substances align, all the rest of the substances must cancel out. If we look closely, B2O3 and oxygen gas are both in a position to be canceled out because they exist on both sides of the equations. At first, it would appear that the water vapor in the second step would cancel with the water in the third step. However, if you look closely, you will notice that the water in the second step is in the liquid state. Therefore, these two are not equivalent, and we now know the reason for that 4th step that was included in this Hess's Law problem. The 4th step is going to allow us to cancel out the water vapor as a reactant and the water liquid as a product. That 4th step must be multiplied by 3 in order to allow for both to cancel. Now all substances not being used in the overall equation are canceled, and the enthalpies can be added together. The change in enthalpy in the overall reaction is 36 kilojoules. Now, it is not unusual to see 3, 4, or even 5 or more steps in a Hess's Law problem. A systematic approach works really well. If you can account for all the substances in the steps, it is a really good way to double-check your work as well. And on that note, I conclude our first thermodynamic video.